Algebra 2 with Mr. Clausen. Today I'm going to introduce a new unit on quadratic functions, and to get started I want to look at how to classify quadratics and give you a brief introduction on parabolic analysis. And so specifically what I'm going to do is get into classification of functions a little bit and how we can look at functions and determine whether they're linear or quadratic and so on. And then also talk about some important points on a parabola, which is the graph produced by a quadratic. And so specifically we'll look at how to find a vertex and axis of symmetry, and then look at how to find corresponding points on a parabola. So with that said, I want to get into classification of functions, because general function notation generally has a format where you place the highest powered term first, all the way down to the lowest powered term, or the constant. And so far, all we really have gotten to is this idea of linear functions, or more specifically slope-intercept form, which is in what we would consider standard function notation. But we generally rewrite this as mx plus b. And we know this to be a linear function, mainly because the highest power term that is present is a linear term. And so where we're expanding a little bit with quadratics is if we look at function notation and we want to do standard function notation, this simply involves, like I said previously, arranging all your terms from the highest power to the lowest power or constant term. And so now what we'll notice here is that you have the constant term here, you have the linear term here, and then you have the new quadratic term, which is this a term here. And so we can look at an example like g of x. We can distribute this -7 if we rearrange it in standard function notation and go -7x plus 28 for this given function. We can look at this and say that it has a constant term of positive 28 and a linear term of -7x, and there is no quadratic term. In saying that there's no quadratic term is something you generally wouldn't say simply because it's absent, but because of its absence, we see that the linear term is the highest powered term because there's only x to the first power here. So as a result, this function is a linear function. And this is important because the highest powered term will dictate the overall behavior of the function. If with a linear term, you will just get a straight linear line. But if we look at something like f of x here, where f of x is equal to x squared minus 7, we have the constant term. There is no linear term, and we generally don't go out and state that there's no linear term, but there is a quadratic term, so we will state that here, that there is a quadratic term of x squared. And as a result, since there is a quadratic term, it is the highest power for this specific function, we can say that this is a quadratic function as a result. Since this is the highest power term, we generally can look at something like this and we can understand that this function is going to create this parabola, this U-shaped function as a result. Now, something to be careful of, I put this example in here for a very specific reason, and one is that you may see an x squared term here, and part of the reason that we like to rearrange it in the standard function notation, like it's written up here, is that if anything's going to cancel out, right, you can see it clearly unfolding and you know what type of function it is that you're dealing with. So even though I look at this function and I go, oh, there's x squared, this is obviously quadratic, it may not necessarily be the case. So one thing that we're going to practice a little bit in this lesson is just practicing our distribution. All right, and if we do something like this, we'll get y is equal to x minus x squared. We'll get minus 1 plus x squared. And one thing you'll notice here is that the x squareds are present in their opposite forms, so that these guys will cancel. And this will just equal x minus 1. So we have our linear term here of x, and we have a constant of -1. And so therefore, this is a linear function, not a quadratic, simply due to those x squareds canceling out. So something to just keep in mind, since we've opened up the classification of functions here to go beyond linear functions, we're going to need to take into consideration those higher powers, and simply by looking at the highest power term, you can understand the general behavior of a function. So now what I want to do is identify some important points on a parabola. And the first point that I want to talk about is the vertex. And the vertex is indicated by the minimum or maximum point that is at the very tip of the parabola. Okay, and so the vertex in this case is the lowest point. And this is pretty indicative of any parabola where the quadratic term is positive. So for example, if your standard notation for a quadratic, or for any function for that matter, is the ax squared plus bx plus c, if the a term is positive, then you will have an upward opening parabola. And this specific parabola has a function of x squared minus 4. And I'll get into a little later how I actually know that. That's for another video. But I can see that the a term is greater than 0, and so therefore the parabola opens upward. If you have a downward opening parabola, this occurs when a is less than 0. And so in this case, you would have a downward opening parabola, and the vertex would be the absolute maximum point instead of the minimum point. So just something to keep in the back of your mind. It's something that we'll go into in more detail later, but just to give you that brief synopsis right now. But the second thing that's really important to know is how to find the axis of symmetry. And the axis of symmetry always passes through the vertex and would look something like this. So your axis of symmetry is a vertical line that represents where you split the parabola in half, or it is the mirror image. And so one of the things you should notice here is that as you go along the parabola on one side, its mirror image is on the other. So if you were to fold this parabola along the axis of symmetry, the lines would directly lay on top of each other. And that is true of any quadratic function. They always make these mirror imaged U-shapes that occur regardless of the a term that is present here. So let's look at this other function I have here. So you may look at this, and I'll just say that -1, 0 is the vertex indicated by this green dot here. The axis of symmetry passes through the vertex again, and you may be asked to identify the axis of symmetry. So we know that x equals equations generally represent this. So we see that it passes through x at -1. So the axis of symmetry is equal to x equals -1. This describes the line that reflects one half of the parabola to the other. And the other thing I want to point out here is that if we are looking at points, because of this knowledge of the axis of symmetry, if we have a point like, let's say, A here, and A can be identified as 2, 0, you can have a corresponding point which is represented by the other side here. And on the other side, we can have a prime, let's call it, the corresponding point of -2, 0. which will be indicated by this orange dot here. And the thing that you should notice is that corresponding points have an equal magnitude from the axis of symmetry when the y value is the same. So when y is equal to 0, you can potentially have a solution for x at 2 and -2. So that's a really unique thing about quadratics, is they can have more than one solution for each given output of y. And so we'll notice here that the distance from the axis of symmetry to this corresponding point is 2, and the distance from the axis of symmetry to this corresponding is also 2, and that relationship will always hold true in these given circumstances. So if you are given a couple points along a parabola, you can go and figure out the corresponding points, assuming that you know what the axis of symmetry is. So let's look at a couple other points on this other graph. So let's say we have these 2 points pop up, and we label this as B, and B is 0, 1. And let's label this point as C, and let's identify this as -3, 4. And so I can see that point B is 1 unit away from the axis of symmetry. So if we go 1 unit away at that same y value, we would see that the corresponding point of B, which I will label as B prime, is equal to -2, 1. And if I go onto the other side here and I want to identify a corresponding point of C, right, we're going to go across the mirror image. It's 2 units to the axis of symmetry, so we go 2 units again. C prime would be, okay, 4 is going to be the y value, but the x value will equal 1. And so what you'll notice here is that as long as you travel horizontally across the point to the other side of the parabola, you can find what is referred to as these corresponding points, these orange points that I'm putting on the graph. And this is important to keep in mind, because I'm going to give you some examples in the homework where you're going to have to draw some graphs. You'll be given a couple points, and then you may have to use those points to find a corresponding point on the other side of the graph to create enough data to model it, to do a quadratic regression, which is going to be what we're going to talk about in the next video. So with that said, I hope this gave you a brief understanding of what a parabola is, how to identify a quadratic function, and how to identify some of these important points that you will need to be able to find. So with that said, let's do some math.